Okay, so what we're doing now, what we're going to be doing for the next week or so is something called the calculus of residues. Okay, so the setting is that you have an analytic function, and it has an isolated singularity at some point. Okay, so it's isolated singularity at some point z naught, so in that case, you have a Laurent expansion. In some annulus, right? So you have this point c naught, and you have some expansion in the disk minus that singularity, right? So so you have something like f of v equals so the power series part. And then you have what's called the principal part, the negative terms of negative powers, right? Where v sub n, as you recall. So this is all stuff you know. These guys are calculated by taking these integrals. Over some circle, over some gamma that is some simple closed path going around z naught, right? And the thing that you notice, so in particular, B1, that's the one associated with the negative 1 power, right, is just the integral of f, right? The integral 1 over 2 by I times the integral around that thing. And so we pointed this out before that if you want to if you're able to get the Laurent series by some other method, then you can get this integral. And this thing we call is called the residue of f at the isolated singularity z naught. So for example, somebody says, here's an integral e to the 2 over e theta I e to the I theta d theta, right? Maybe if you're in calculus, you'd say, oh my gosh, I don't think this is possible. But now that you've had some complex analysis, then you say, oh, well, you just say, well, I recognize that this is actually the same thing as the integral of e to the 2 over z dz around, say, the circle of radius 1 around the origin. Right? You see it. Right? This is just. These are the same thing. Right? Okay. And so you'd say, okay. In that case, what I need to do is get the Laurent. To get this, I need to find the Laurent expansion of e to the 2 over z. Right? But you know what that is, right? E to the 2 over z. You need the Laurent expansion of e to the 2 over z around 0. Well, that's just going to be 1 plus 2 over z plus 1 over 2 factorial 2 over z squared plus etc. Right? You just use the expansion. You just use the expansion of e to the z. Right? Plug in 2 over z, and then you can read off the residue. Right? The residue is 2. Right? So the answer is 2 times 2 pi, 2 times 2 pi, right? 1 over 2 pi. This over 2 pi I will be 2. So this thing is 2 times 2b1, right? Which I will not simplify further. Right. So this is pretty cool, right? It's sort of cool, right? That we can do these sort of integrals. These sorts of integrals are now trivial. Okay. Okay. So right. So if you have a single isolated if you have a single isolated singularity, right, and you want to get this integral around it, then what you're going to do is say, I'm going to look for the residue, right? I'm going to take the Laurent expansion around that point and just find the residue, and that will allow me to calculate this integral. Okay, and if there are multiple, so we have something a little bit more general, and you have something even more general than that, which I'll maybe state next time. So this is what's originally called the Cauchy residue theorem. And so if you have function f, which is analytic on some domain, A, with isolated singularities, finite number of isolated singularities, z1 through zk. If C is a, say, simple closed contour, around all the zi, and its inside is inside A. Right. So you have some, you don't have something like a big hole. You don't have something like this. Right? You don't want C to you don't want C to have a big hole inside of it. Right? So the interior of C should be inside of A. The interior of C should be inside of A. Okay. Then the integral over C turns out to be just the sum of the residues at those places. Any question? Yeah. So what's the proof of this? What's the proof of this? Can anyone see the proof of this? And you have a few, there's a finite number of singularities. Right? And you have this thing, C going around it, right? And you want to get the integral of this. So you already know that if we integrate around any little circle around the singularity, what do you get? You get the residue. Well, you get some constant times the residue, right? Right. So you just take a bunch of little circles. Right? You take a bunch of little circles, right? And then you say maybe the way to do it is to say you make some path by going with this. Something like this, going and then that path is homotopic to the big path, and so the integral over the big path is the integral over the small path. But the integral of the small path is just the sum of the integrals, sum of these integrals, because these paths are crossed in both directions and they cancel off, right? And so you get just the sum of the residues. Okay. So that's the proof. Do you want me to write it out? No. Good. Okay. So yeah, so you just use you just use the deformation. You just use the deformation theorem plus the result that we plus the result for one singularity. Okay. So here's the proof. Yeah, question.
This is kind of a weird question, but like, what is the intuition that the term residue is trying to capture? Like, what is left over?
Yeah, it's sort of what's left over, right? Because when you remember how you get the residue, you integrate the function over the circle, and everything except for the -1 term vanishes. Remember, so it's just what's left over.
Okay.
Right. Like you use the uniform convergence, right?
Mm-hmm.
So you can replace this thing by its Laurent series. Then the integral of all the terms, right? All the terms are going to have antiderivatives, except for the -1 term, which has this logarithm guy, which isn't continuous, right?
Mm-hmm.
The logarithm, so what -1 guy doesn't give you back 0. It gives you some number, right? And that's the residue.
Okay.
Right. There's some joke about Cauchy's dog leaving a residue at every pole or something like that. I don't know. Go look it up. There's some joke about this.
Sorry, could you remind me why you get zeros at the ones with antiderivative?
But remember, if you integrate, so you're going to get things like this: z minus z naught to the n dz around a disk centered at z naught, right? And remember, when you did this calculation, you get 0 every time, except when n is -1, right? In this case, we did this calculation like in the beginning of the course. You end up with 2 pi I, and in all other cases, you get 0, right? So all the term, when you integrate this thing, then everything vanishes except for this one term, like the B1 term.
But then here there's a multiple of them. Or am I misunderstanding that?
Yeah, so this, I'm sorry, what I meant was if you have a single isolated singularity.
Okay.
Yeah. So, right, in the case of a single isolated singularity, then you're gonna, right, so then you're gonna pick up that residue. Now this one is, you have a bunch of residues, right? You've got a bunch of poles here, right? And you're integrating around all of them. Well, the integral around this whole loop is just going to be the sum of these integrals, each of which gives you the residue at that point, at that pole.
So, and are we looking at a different Laurent?
Yes, that's right. So at each place, you're going to have a different Laurent series.
Okay.
Right. So it's sort of a pain because you'd have to find the Laurent series at each pole, and then you'd have to say what's the residue at each one, and then add them up. Okay. So we'll do an example. So somebody says, here's an integral. Right. I'd like you to integrate this on the circle of radius 3 around the origin. And you see that this thing has poles at 0 and at 2. So this has poles at 0 and 2. So maybe one way you do it is to so here's one possible approach. you'd say you could take a partial fraction decomposition. And when you do, you find that you get negative a half over z plus 3 halves over z minus. Okay, so you take a partial fraction decomposition, and lucky for you, it turns out to be something like this. It's not lucky. That's obvious. You get something like this, and then from here, what do you say when you see something like this? We're trying to find. Think of what we're trying to do, right? We're trying to find the residues of this function at 0 and at 2, right? So.
Or that's just a single, the first term, or of the wrong expansion, like the negative first term.
So, say one more time, Michael.
I mean, so that's just like the z of the negative first term of the wrong expansion itself. So don't you know that the residue is just the integer or the value on top?
Mm-hmm. Okay, so in fact, turns out that the residue at z is the residue at 0 is just going to be negative a half, right? Because this thing here is an analytic function at 0, right? This thing is an analytic function. So you're clever. You say, oh look, this is an analytic function at 0. So what I'm going to get is I'm going to get this thing, and I'm going to get the expansion of this thing around 0. Well, that's just going to be some sort of Taylor expansion. That's not going to contribute to the residue. So you would just read it off and observe then that the residue at 0 is negative half, and the residue at 2 is 3 halves. Right? So you got lucky, you read it off, and you say, okay, so I know that the integral is going to be it's just going to be 2 pi I times the sum of those residues. You get 2 pi I. Okay. If you were not observant, then maybe what you would do is say, oh, okay, now I've got this thing and I need to expand it. I need to get the expansion around 0, and I need to get the expansion around z equals 2, right? And then maybe you do some work. So you say get the expansion. Say, okay, well, here's maybe one way you might approach it. You'd say, oh, look, I'm gonna rewrite this as negative 1/2 times 1 over 1 minus z over 2. I'm gonna rewrite that 1 over z minus 2 in this way, and then use the geometric. This as a geometric series, right, which is valid in the circle of radius 2, right? And so so that's summation 1 over 2 minus 1, c to the n. Right, and so you'd get that the expansion would be like this: negative 1/2 over z plus 3 over 2 to the n c to the n. From 0 to infinity. And then you would realize that that thing that we just added on doesn't affect the residue at all anyway, and so our residue is still negative 1/2 at 0. Okay. And if you're completely obtuse, you keep on going and get the expansion around 2 also, and then realize that that didn't help you at all. Also, okay. But anyway, whether you're clever or not clever, one way or another, you get the answer. As long as you persisted, that's a good moral. Yeah. This is just basically the moral of my undergraduate education. You didn't have to be the genius as long as you spent your entire waking life inside the library.
It's a big if.
Okay. Everyone all right? Okay. So let me show you a couple of tricks of computing residues. The one cool one is something called the residue at infinity. Yeah, I spent my entire first semester at Princeton, I think, being sort of stunned at how smart everybody was. And then after that, I just spent my all my waking hours in the library and did all that. So. So you're gonna like this. It's pretty cool. Suppose that is analytic on all of the complex plane, excluding a finite number of singularities. One of my fond memories of my first semester at Princeton was this other, being completely lost in this class, which was on, abstract, which was linear algebra, but from an entirely abstract perspective. Like there were no matrices in this class, no matrices. The determinant was not defined using matrix, but rather using matrices, but rather using alternating forms. Anyway, a couple of weeks into the course, there's this guy, the same guy I probably mentioned before, the guy who doesn't take notes, who's the smart guy. He's sitting there and he raises his hand and says, "So that's a non-canonical isomorphism." And Wiles, Professor Wiles says, "Yes, that's right." At that time, it wasn't even clear to me what an isomorphism was, let alone why an isomorphism would be non-canonical or canonical.
Wait, was this graduate school or?
No, undergraduate.
Undergraduate.
Yeah, so it's my first class in college.
Didn't you start as not a math major?
That's right, I wasn't a math major at this point. Yeah. I was deciding between English and math up until my second year.
Have you ever thought of combining the disciplines, becoming like a math English professor?
Well, I can sort of do that here, actually. At Scripps, you have the chance to teach in the core, this thing called the core, and you get to read all this, literature and philosophy and stuff. It's a lot of work for somebody who doesn't have that, who's not familiar with that. But it's not unfamiliar for me because that's what I like. That's something that I like.
You were teaching English.
Huh?
You were using English. You were teaching in English.
I'm teaching in English. Yeah, that's true. I'm glad you think so. Okay. Suppose F is analytic on all of C, excluding a finite number of singularities. Let gamma denote any contour, let's say simple contour around all of z lines. Okay, and all of our contours are going to be oriented positively, like counterclockwise, unless we say otherwise. Then the integral over that, right? This is what we calculated, what we were just talking about. It's the sum of the residues. But in fact, there's a way of calculating it in one move. Okay. You calculate rather the residue of this function at 0. So instead you have this related function, and you calculate the residue of this guy at 0. And it turns out that is going to be the sum of all the residues. Okay, and this thing is called the residue of f at infinity. Now we'll explain why this is true first, and then we'll explain what this has to do with. We'll try to explain what this has to do with infinity. I think I sort of messed it up in my notes, but hopefully we can wing it. I can wing it. Give you an answer. Okay. So you have a bunch of singularities, right? And you have some path gamma going around them. Let's see, be a large circle, just a circle of radius r, centered at 0. That contains gamma. So you take some circle C. That goes around everything. Okay. Okay. And you know that F is analytic outside here, right? These are the only singularities, so it's analytic outside. And so we take a Laurent expansion. Take Laurent expansion. In the annulus, and you know what we want, right? We want C negative 1, right? Because that will be that's the integral. That's the integral that we're looking for. Okay, and so what we need to do is show that C negative 1 is equal to this. Okay. So observe that if we look at f of 1 over z, that's C, so then 1 over z to the n, and from negative infinity, positive infinity. And that's valid where 1 over z is between r and infinity. That's to say, it's valid where z is between 1 over r and 0. And then you notice that, so 1 over z squared, f 1 over z, right, is going to be summation c sub n minus 2, 1 over z to the n, from negative infinity to positive infinity. Because I'm shifting the index by 2, right, by multiplying by this, right? And what you see is that the residue of, so observe, the residue of this thing at z equals 0 is c negative 1. Which is what you're looking for. Okay, so just a simple. There's nothing fancy going on with this equality. Right? It's just a sort of a calculation, a manipulation. Right? Say, okay, let's take the Laurent expansion, and then let's create another function, create this other function out of it. Right? Notice that if we shift the index on that guy, then the negative one coefficient of the Laurent expansion of this guy at 0 is equal to the integral of your original function over that disk, over that circle. Okay. Is that clear? Just the manipulations of it? Are those manipulations clear? No.
No, not quite.
Okay. So let's say it again. You take the Laurent expansion, right? And then you're gonna say, let's look at f of 1 over z. That's this, right? And where is that valid? That's valid where 1 over z is between r and infinity. In other words, where z lies between 0 and 1 over r. So, right. So what you're doing is you're creating a function. You're creating a function of z, right? You're creating a function of z that's valid in the inverse of this. Right? Okay. So the original function, right, was analytic outside here. The original function was analytic outside here, and you create this new function, which is going to be valid on the inside of the disk with radius 1 over r. And so remember, what you're looking for is c negative 1, right? You'd want to find c negative 1, and you say, oh well, look, c negative 1 is in here. If I shift this thing by 2, then c negative 1 lines up with the residue of this thing, right? So when n is equal to 1, right? What's the residue of this guy? What's the residue of this guy at 0? Well, it's going to be the coefficient of the negative 1 term, right? In other words, the coefficient when n is 1, right? So that's going to be c negative 1.
Wait, shouldn't it be c at negative 3? Because
no, because I've written 1 over z to the n, right? So I want n to be 1, not n to be negative 1.
Oh, okay.
Right, because the residue is the coefficient of the z to the negative 1 term, right? Well, the z to the negative 1 term is when n is 1 here.
Ah, okay.
Right, so that's when, and the coefficient then will be c negative 1. Okay, and so I've shifted, the point of adding on this z squared is to is to shift the C negative 1 coefficient so that it becomes the residue of this thing. Okay, right? If we didn't
In
do
other
that,
words, so that they both have the same C negative.
they both have the same C negative 1.
Okay.
Yeah, so that's why you need to add on this 1 over Z squared. So, and then you say, well, look, you know, that C negative 1 is the residue of this new function, and that's what we were trying to show, that the residue of this new function that we made up is the integral.
Yeah, Mike. So then this is the difference between how you set up this problem and when you typically do a line expansion for an isolated singularity, is that here you have a gamma that contains all of the singularities. When it was an isolated singularity, by default, your lower bound was essentially 0.
Yes, that's right. Yeah.
But here, then you have to choose like a z such that it contains all, like a z such that it contains a curve that includes all of the isolated singularities as your lower bound instead to find the validating of this. So you're given like a gamma that you know contains all the singularities as long as C contains that. Fine.
Yes, that's right. That's right. So let me do an example. Let me do an example, and I think that will make it clear how to use this. Okay, actually this is the same example. So z plus 1 over z minus 2. So again, you know, we're integrating around a circle. We have these two poles, and you know, maybe there are many poles, but in this example, there are only two. Okay. And so it says, well, what we need to do is find the this is going to be 2.9 times the residue at infinity. Right? The residue of this guy at infinity. So the residue of 1 over z plus 1 over 1 over z minus 2, everything times 1 over z squared. Okay. So you have your 1 over z squared, f value 1 over z. A little bit of algebra allows you to write this as 1 plus z over z times 1 over 1 minus 2z. One plus 1 over z times 1 over 1 minus 2z. And then from there, you'd say, okay, you know, I want to find I've got this thing, and I want to find this Laurent expansion about 0, right? And so, sort of obviously, you're going to do the geometric series trick here, right? You're going to multiply that geometric series by 1 plus 1 over z. So you end up with 1 plus 1 over z times the geometric series. And so the only 1 over z term, you get is 1 over z, right? Right? You see that the 1 over z term has coefficient 1. So it's this, and so you end up with 2i. So you need, instead of calculating the residue at multiple points, you calculate the residue at a single point of this modified function.
Just notationally, why? I mean, why can't you just? So if there's a path that contains all the singularities, but you could just, I mean, you could just integrate over the circle that contains the path. Anyway, I mean, that's essentially what you're doing in this case, is integrating over a circle that contains all the singularities.
Yes.
But there could be any number of paths inside the circle that contain. I mean, in this example, it would be like, see, you don't even need gamma in this case for the computational example.
That's right. That's right. I mean, you could say that this is gamma.
Yeah, exactly. So it just seems
Why did I mention
like
gamma?
defining twice, defining.
You don't need to mention
Okay.
gamma. I mean, but if somebody gave you something like this,
Okay.
I guess
Yeah,
it's
I mean, that doesn't really. If
Yeah, it doesn't-
If you're given a strange looking curve.
then you just say by deformation you can deform it out to a circle. Okay. Okay. So sorry. Let me see if I can explain this in a different way. I haven't really thought this through yet, so when I mess up, I'm just gonna skip it and I'm gonna erase it from the video. But see what is really going on here? What's really going on here? So, think like this. You have f that is valid, or it's analytic on outside some disk. This is basically what you think of as a neighborhood of infinity. If you're thinking about the Riemann sphere, right? Thinking about the Riemann sphere, right? Then outside of some R basically means that you're taking some latitude, right? Taking some latitude, and you're looking at everything above that latitude, right? So it's a neighborhood, it's some neighborhood of infinity. Okay, so now W would be Z inverse. So then one has an expansion, a Laurent expansion. W equals summation C times W. Right, which is valid, so valid in a neighborhood of 0. Right, so you do a change of variable. Okay, you do a change of variable. Say, okay, well, I'm going to think of this value as I have this Laurent expansion around 0 in the in the reciprocal neighborhood, right? So then the residue of this guy at W equals 0, which you think of as the residue Z equals infinity, is going to be 2 pi I over equal of f of W dW around some disk, right, around the orbit, right, where rho is between 0 and 1 over r. but changing variables back, what do you get? Well, you're going to get this 1 over f of 1 over z dw. Well, dw is going to be negative 1 over z squared dz. Right. Right, because w is z to the negative 1. So dw dz is right. It's going to be negative 1 over z squared dz. Negative 1 over z squared. Excuse me. Right. And what's going to be the domain of the integration? What's going to be the contour of integration? Well, it will be over the circle of radius 1 over rho, but it will be going in the opposite direction. Right? It will be going in the opposite direction. Right? Because as right, if W is rho e to the I theta, then 1 over W is 1 over rho e to the negative I theta. Right? And as this guy walks around counterclockwise, this guy's going to walk around clockwise. Right? So you get the integral of the loop in the opposite direction. Right? And so what you get is that that allows us to get rid of this negative sign, and we get 1 over z squared over z dz, which is to say the residue of this function around 0 is the residue of f around infinity. So maybe that makes things a little clearer, what was going on. Okay, so let's go on. Let's see. So there are a couple of sort of simple results of how to calculate residues. There are other tricks of calculating residues. So, this section, as we said, were a bunch of tricks. So here's one of them. It's a very simple one. Calculating residues at simple pools. So suppose you have two functions, p and q, and they are analytic at some point, and you know that q is equal to 0 there, and you know that p is not equal to 0 there, and you know that p prime is not equal to 0. Okay. So then you look at the quotient p over q. Well, it's going to have a pole. Right? It's going to have a pole at C0. Right? In fact, it has a simple pole because, as you see from here, q has a simple 0. Q has a simple 0 there. Right? Q doesn't have a 0 there. Right? So you've got something without a 0 and something with a simple 0. You take the quotient. This thing is going to have a simple pole with residue p over q equaling p of z naught over q prime z. This is pretty simple. It's basically a consequence of so you know that since Q has a 0 of order 1, we know that Q can be written as, z minus z naught times some analytic function that is non-zero at z naught. G is analytic. And G at z naught is non-zero. Then, sort of obviously, P over Q is going to be P over G 1 over z naught z naught. Where this is some analytic function, right? Analytic z naught and non-zero. And what's the residue? The residue of the residue of this is just going to be phi. It's just going to be phi of z naught. Phi of z naught, which is P of z naught over G of z naught, but that's the same thing as P of z naught over Q prime z naught. Right, because when you take the derivative of Q prime, Q prime z is going to be anyway, this is not a particularly remarkable theorem. If you're not excited, that's good. So the book actually gives like a string of the results along the same line. So let me just show you what the next one looks like, but I'm not going to prove it. G and H analytic of z naught, and you know that G of z naught is non-zero, H of z naught equals 0, H prime of z naught equals 0, H double prime of z naught is not equal to 0, right? And you're going to look at G over H. So G over H has, well, you look at it, it has a double pole, right? It has a double pole. Z naught with residue, and then they give this sort of god awful residue. So here it is with residue 2 G prime z naught over H double prime z naught minus 2/3 of G z naught H triple prime z naught over H double prime z naught squared. Okay, so and then they say you can go farther with higher for triple poles. They're also more funny. So we're not even going to walk. We're not going to walk any farther down this path. I think instead of doing that, something that's sort of simpler. is to use the characterization of poles. So here's another way of calculating residues. Residues of poles. So recall, right? If F has an isolated singularity, Z naught, and then F has a pole of order n at Z naught, if and only if F equals phi of Z over Z minus Z naught to the n for some analytic such that phi of Z naught is non-zero. So this is a theorem that we proved before. If you think about it in the context of residues, then it gives you sort of a useful, you can make a useful observation. Let's see. Right. So observe. You know that F looks like this, and so what you can do is take the Taylor expansion. Say, okay, F of Z then is the same thing. Right, of course. You take the Taylor expansion. You take the Taylor expansion of phi, right? So, and what you get is k plus m Z naught over k plus m factorial Z minus Z naught to the k. K from negative m to infinity. Just as a consequence of the Taylor expansion of phi. And you write it like this. And what does that tell you? Well, that tells you that the residue of F at Z naught is going to be phi to the m minus 1th derivative of phi at Z naught over m minus 1 factorial. So if you know the order, of the pole, if you can figure out the order of the pole, then this gives you, a way of determining the residue in terms of this function phi. So let me do an example. Some simple examples. F of Z is, say, Z squared plus 2 over Z minus 1. So you look at this thing and you say, okay, I know that this thing has a pole of order 1 at 1, right? It has a pole of order 1 at 1, right? So what's the residue? The residue is just going to, we write this as, right, so phi is Z squared plus 2. Right? The residue is just going to be phi itself evaluated at 1 over 1 factorial. Right? So that's 3. Oops, over 0. Right. So that's maybe better than than finding the Laurent expansion and working it out. Another example, f of z is, say, z cubed over 2z plus 1 cubed. So So you would say, okay, well, I know that at negative a half, this thing has a pole of order 3, right? So pole order 3, negative a half, right? And so we rewrite this as say z cubed over 8 times 2 plus a half cubed. Right? This thing is our phi. Right? Since it's a pole of order 3, we know that what we need to do to find the residue is to take the second derivative and evaluate it at negative a half and divide by 2 factorial. Okay? So you take the second derivative of this guy, and you evaluate it at the point, and you get negative 3 resistance. Another example, sort of combining this with the residue at infinity trick. Somebody asks you to evaluate z cubed equal 1 over z, 1 plus z cubed, over the circle of radius 3 centered at 0. Okay. So you know that this thing has three simple roots, right? The cube roots of -1, right? inside here, and so maybe you could, one way to do it is to find the residues. We're going to pull off the residue at infinity trick. So okay, let's call this thing. Then if we look at 1 over z squared f of 1 over z, what you end up with is e to the z over z squared 1 plus z cubed. So, and we want the residue of this thing at 0. We want the residue at 0 of this thing. And so we say, okay, I'm going to take this as my, this is going to be my phi, right? And this thing has a pole of order 2, right? So pole, let's call this guy G. G has a pole of order 2, that's 0. So we evaluate the first derivative of this guy at 0 over 1 factorial, which turns out to be 1. Okay. And so this turns into just 200. Okay. Yeah.
So, like the overarching intent is to be able to evaluate these integrals because they also happen to be the first terms of the Laurent expansion.
Yeah, sort of. Yeah. So I have to say that in some sense this is a bit contrived, right? These are all things that that happen to work out for us. So from a this is not the high point of complex analysis. This is sort of like a consequence. It's cool. It's useful. I think this is part of the bag of tricks of people who who need to integrate things. But it's certainly not the high point. Although apparently Cauchy felt that the calculus of residues that he created was far more important than the integral formula, where from the modern perspective, the integral formula is really the great insight. Okay, so more of this next time, more contrived integrals next time. Don't miss it. No, I hope that it will be kind of interesting.